autonomous driving. Before we get started, can you just confirm in the chat if you see my screen and hear me all right? Okay, thank you so much. One thing that may happen when I'm showing a few things is if my screen gets stuck, I will just pause for a moment and I'll just quit some background processes. But I have done as much as I can to make sure that the screen will not be freezing. But if it so happens, we will fix it on the go. So today our goal will be one singular goal, understanding about action chunking transformer, ACT, and build an ACT policy ourselves for self-driving. But today we will not be looking at a self-driving car, which is physical, but rather we'll be going back to our environment, which we discussed in the last lecture, which looks something like this. So by the end of today's lecture, you also should have something which is shown in this video. I hope you can see this video kind of okay. So I'm just going back a few steps. So look at the way in which it is driving. So this map, which has two ways to drive from your starting to ending position, through the left or through the right. And ideally, depending on the language intent, the car should be able to navigate itself. So right now the language intent is right. So it is navigating through the right-hand side path to the end. Or if the language intent is left, it should be able to drive on its own, right? So this, with the help of action chunking transformer, with language intent, and with one additional thing called conditional variational autoencoder. We'll discuss all of that during today's lecture. So by the end of today's lecture, everyone should have something like this ready. Now, to save a little bit of time for all of us, I'm just jumping the gun one step so that some training can happen while I'm speaking. So I want all of you to first open this link. Just let me put this in the chat. Okay, there is a question. Is this course advanced or intermediate course? In my opinion, this is intermediate course. If you know basics of transformers, you should be able to follow this course. Otherwise, I have put the required prerequisite material regarding transformer in the course dashboard. But can everyone open this link? And what I want you to do is, I don't want you to this time collect training data because I have already collected a lot of training data with my colleagues in the office. There is good enough amount of training data. All I want you to do is click the training data folder icon here, which will download the training data to your downloads folder. And then click the Colab notebook, which will download this Google Colab notebook. And then if you have Google Colab Pro, use A100 or whatever GPU is available to you. Otherwise, use whichever advanced runtime you have except CPU. You may already have T4 GPU available. I don't know. I forgot which one was available in that Google Colab free version. Whichever is available in the free version, go with that. Then once you have the notebook setup, run all the cells, click run all. And at one point in this particular block of cell, it will ask you to upload the training data. There will be an upload button. And that is where you have to upload the training data JSON files, which you download from this training data link. This is all I want you to do right now. So just do it in 1 minute and let the training happen in the background, so that by the time when we actually discuss this, you already have a trained model downloaded. So once the training is done, in the last block of code, it should automatically download a model.json file, which will be your trained model, which will be there in your downloads folder. So I just want you to go through this process just to see how much time training takes. Even in the worst case, if the training takes a long time, I already have a trained model.json, so you can use it directly. But I wanted everyone to just run this training once. We will go through the code in detail during the lecture. So just make sure that the training is running in the background while you are listening to the lecture. Okay. So now the question is, if we are a human expert and we show the neural network how to drive, can we teach the neural network so that the driving can happen autonomously? Now, there are a few different options here, right? So in the last lecture, we had discussed two roads. One was this forked road, which had like a fork, meaning there are two paths through the left and path to the right. And you can drive it yourself like this, and you can record, this one I am driving right now. So you can record sessions. So I showed you how to collect the training data, which I don't want you to do. I'm just saying. I also have another map, which is this map. So this map is like a simple curved road where there is no language intent required. The only thing which we have to do here is driving along the road. So for a case like this, where my only intention is just to drive along the road, if language intent is not there, in your opinion, what model could we use for training such that the car can drive itself? What could be the model architecture? Because there are several different options, right? We don't necessarily need a VLA. So let me just write it down. We have a curved road. Let me just close this. And we have a forked road. In forked road, there are two options. You could either go through left or go through right. In curved road, there is only one option, just drive. Just drive along the road. Now let's talk about curved road for a moment. Okay. If this is the kind of track map on which we are driving, do we really need VLA? Do we need the language part? We really don't need the language part because the language intent is just, there is only one intent, just drive. So language is actually not helping us with anything. We just need vision followed by action. Okay. So somehow the vision, and what is the vision? Vision is simply the pixels corresponding to what the car is seeing. So for example, this little inset, what you see here is the vision part. It's a 128 by 128 pixel input, which we can feed into the neural network. It's as if what the car will see if you are sitting inside the car. I had shown you how to switch the mode to the driving mode. So third person mode is like if I press C, right? So now this is the third person mode. This is what the car will see. If inside the car, there is a dash cam. So this we can save as an image file as we discussed in the last lecture. Now the question is, this image, let's say this is 128 pixels by 128 pixels. At the end of this, at the end of something, at the end of some model, should be converted into some actions. In this particular case, what are the actions? In this case, there is a question, what about the obstacles that come while driving? Of course, so there are many complex situations. We are first starting with very first basic principles, just simple driving. We are not thinking about obstacles. We are not thinking about multiple decisions to make. Only decision is simply to drive on an empty road. This last thing, which are the actions, what are the actions? In our case, in this particular website where you are driving, the action is forward, left, right, or back, right? So there are 4 actions. So whatever is predicted at the end will have 4 items, one corresponding to left, one corresponding to right, forward, and backward. So somehow this image, 128 by 128 pixel image, we'll have to convert it into this. Speed is not there because I have not manually programmed the speed. Speed is just an artifact of you pressing the forward button sequentially. So if you press forward button continuously, speed will keep increasing. So it's just an aftermath of you pressing the forward. So you don't have to predict the speed. Speed is just a consequence of your action. So my question is, this model, if the only input is image, and if the only output is these 4 actions, and let's say we are not even chunking the action, we are just predicting one action at a time, what could this model be like? What can it be made of? It's really not image classification because you are not classifying it into anything, right? These are not classes. It's almost like a regression. So we can use like convolutional neural network. So let's say my input is of dimension 128, 128, 3. What is 3? 3 is the RGB, 3 channels. I can have a convolution operation which will convert, let's say 128, 128, and there will be a batch dimension also. Let me just write that also in case if this is a neural network training, we'll have a batch of images. So batches batch dimension, followed by spatial dimension, followed by channel dimension, then 2D convolution, and that could convert this into B comma 64 comma 64 comma, and let's say that 3 becomes 6 or something. So in general, after convolution, channel number of channels will increase and spatial dimension will decrease. And then there will be an activation function following this. So let's say activation is ReLU. Activation is very important to introduce non-linearity. Then again, we could have a 2D convolution, conv 2D, which will convert this into B comma, maybe 64 will reduce to 32 comma 32. And depending on the number of output channels, this can become 16, right? Like that, you will have 1 or 2 or 3 different convolution layers. So these are convolution operations followed by non-linear activation. Now, at one point, let's say your output looks something like this. So let's say you have one more con 2D, which converts this into B comma 16 comma 16 comma let's say 64. Okay. Now let's say this is your intermediate output after 3 convolution layers. You have a batch dimension 16 comma 16 comma 64. Can you tell me what is 64? 64 is the channel dimension. What is 16 comma 16? It is the spatial dimension, which means the way this will look like is something like this. So this will be 16 by 16. Then this will be another 16 by 16. This will be another 16 by 16. This will be another 16 by 16. Like this, we will have 64 items, right? So this will be 16. This will be 16. And the total number of these things along the channel dimension will be 64. Now, what we want to do is, let's say my embedding dimension is 64. What we want to do is convert this 16 by 16 by 64 into something like 1 by 64. So what we need to do is this 16 by 16, we need to convert into somehow 1 by 1. Of course, there is a lot of loss of information there, but at the end of the day, let's say our embedding dimensionality is 64, which means the spatial resolution we have to shrink to such a small level that it has to become 1 by 1. What operation can you do to take this 16 by 16 into 1 by 1? So Sandeep has mentioned global average pooling. Yes. So basically pooling. You can pool the pixels into one single value. It can result in 1 pixels, 2 by 2 pixels. So depending on your pooling resolution, if it is a global average pooling, you can reach 1 by 1. And like this, there will be 64 channels. Okay. So now essentially what do you have? You have a 64 dimensional vector, isn't it? Because this spatial resolution is anyway 1. So now you have a vector consisting of 64 items. Now what you need to do is, ultimately what you need is something of dimensions 4, because your number of dimensionality of each action is 4. You have front, left, right, back. So you have to somehow convert this 64 into 4. So what you can do is, you can have a multi-layer perceptron, MLP, where the initial layer is something that maps the 64 nodes. So these are, let's say 64 into maybe 128 or 64 with a fully connected layer with ReLU or some activation function. So this intermediate layer can be 64. It can be 128 depending on what the architecture looks like. But the last layer will be how many? 4. So you go from 64 dimensions into 4 dimensions. So what you get out of this, and there will be ReLU also, I'm not writing it, ReLU or some other activation function, there will be a 4-dimensional output. Now these 4-dimensional outputs, the numbers, I want to convert it into probabilities whose values are between 0 to 1. What can I do for that? How do I convert these 4 numbers into probabilities? So softmax is a good thought, but in this case, there is one small caveat which the reason due to which softmax is not ideal. The reason is when you are driving, imagine you are driving a car. When you are giving accelerator, it is as if you are moving forward, correct? And when you are rotating the steering, you're trying to go a little bit to the left or to the right, but then also accelerator is there, which means the forward action can be coupled with right or with left, or forward can be there alone, which means it's not like we are always applying only one action. Even in the game, in the 3D environment, when you drive the car, you may have two actions at once, which means you don't want to convert these four numbers into a probability distribution, which looks something like this. You don't want, and let's say this is left, right, forward, backward. You don't want something like this where these four numbers add up to one. What you rather want is something like this. So let's say this is 0 and this is 1. What you want is between 0 and 1, all these numbers should be between 0 and 1. So if it is left, left can have a high probability. Then right may have a low probability in that case, because left and right you don't press together. But forward may also have a high probability, and backward will have a very low probability. So these four numbers need not add up to 1. It may add up to greater than 1. But individually, these numbers represent the probability for left, right, forward, and back. In this graph, what you are telling the model is just take right. And this is what softmax will result in. But in this graph, what you are telling the model is, or what you are telling the car is, take left while going forward, which means it will go forward and take left. And this is the result of sigmoid. Because sigmoid can convert individual numbers between 0 and 1. It will not, however, convert the whole set of numbers into one probability distribution. So what you really need here is sigmoid, which will convert these four numbers into individual probabilities between 0 and 1. And now you can take the action. So now look at your simple architecture. The simple architecture for this curved road is very simply, you have four convolution layers, 4 or 3 convolution layers, depending on your architecture, right? Followed by max pooling or global average pooling. I can call it as GAP. Following this, you have a multi-layer perceptron, which projects the whole thing into 4 dimensions. Following this, you have sigmoid to convert into probabilities, right? Very simple architecture. All right. So this is the most simplest architecture you can apply for the curved road. This may or may not work really well. So one way for you to test this is, there is a sigmoid is generally used for binary classification, right? Yes, that is correct. And here, what is binary? Here, the fact that the binary is, are you going forward or are you not going forward? Are you going left or are you not going left? Are you going right or are you not going right? So that is the binary. So here, if 50% is the threshold, let's say this is 0.5. The binary decision is in deciding, okay, this is the sigmoid corresponding to left. Is it greater than 0.5 or less than 0.5? If it is less than 0.5, maybe you will say, actually, left action is not there. So this is where binary is coming. Binary is not coming in picking either one of these, okay? It's coming in picking within the action, whether it's greater than, whether it's a high probability action or low probability action. So now, if you go to this link, exp1vla.versal.app, I have already trained the model. It was such a painful thing to train these models. It took me so much time and so many number of experiments. It's still far from perfect. But what you can do is, you can click this inference, and I have made your life so easy by, you can just click load bundle model. It will load the model, and then you can click autopilot, and it should move in autopilot, although in a very, very bad fashion, in the sense that it can barely navigate. Right now it looks okay, but in general it's not. It can go and ram into the trees, because you need a lot of training data showing failure modes. You see, it's now going off road. Then it can hit the building. If it hits the building, it will respawn. So the only way to make a model like this work really well is to collect a lot of training data where you don't just show the expert driving. That is not enough. Yeah, website is lagging because of inference. For sure, it will because you are running the model in JavaScript. So the web browser will lag. That's the reason why I don't want to show it fully. That's the whole reason why I recorded this video. It's so that I don't have to use my browser. So this is the video where I'm using the vision encoder alone with multi-layer perceptron for acting. And one thing is, if the car does not make any mistake, it will go along the road. But if the car makes a mistake, it struggles to come back to the road because it can make mistake at any point. And if you are recording the training data, you have to show a lot of cases where the car makes a mistake and the car comes back by correcting the mistake. That you have to show in the training data. Only then it can learn from it. If you really want to train the model, usually how much data is required to make a car perfect. So in this experiment, what I did is I recorded, this is a loop, right? This map is a loop. So I recorded one loop, and then like that, no, I recorded 3 loops at once, then downloaded the training data. And like that, I had 16 to 20 different JSON files, which means around 45 to 50-ish training data JSON files I had, roughly. Even that, I think the issue is I wanted different type of driving styles. So what I asked my colleagues to do is I asked them also to drive and collect the training data so that I can get their style of driving. So I had good enough training data. What will be even perfect is in this lecture, look at this. Right now, there are around 50 people, right? 40, 50 people. So all of us can drive. You download the training data, and we can upload it into a common folder so that we collectively can have a very vast, very good training data set, right? So that is the ideal thing to do for training. But right now, if you don't want to collect training data, in the website itself, I have provided an option to download training data. When we get fail cases, what does data look like? So in fail cases, data is simply you manually drive the car outside the road, then you come back. Then again, you manually drive the car outside the road and come back. That is how you show failure being corrected. Otherwise, if you always drive in the middle of the road, the moment your car makes a mistake, it doesn't know what to do. So it keeps on compounding on the mistake. Okay. So this is basically the data collection pipeline. You drive your car, you have a bunch of images corresponding to its actions, and then you train the model. I'll show you the model. The model I already discussed, but I'll show you a better looking image. But this is not action chunking transformer yet. So today, what I want to spend most amount of time is in action chunking transformer. But before getting into action chunking transformer, I want to show you some other simpler options, and then I will discuss why we need action chunking transformer. So these are the two environments we will discuss. The curved road path, which is like a loop that goes generally to the left. So you have to drive and turn to the left. So it's like a left-hand side going loop. The second map is the forked road, which has two options, going to the left or going to the right. And I'll tell you the reason why I have picked these two maps. Because in the forked road, there is a language conditioning required. Because in forked road, to reach the target, you can either go through the left or go through the right, right? So that's the reason why I picked these two. In the curved road, that is not needed. So it's the perfect setting for us right now. Now, I'll talk to you about the details of the different architectures that I used. But before coming to that, I think we discussed this last time in the last lecture, action chunking. Why the need for action chunking? The need for action chunking is, and by the way, action chunking simply means instead of predicting the next action, you predict the next 5 actions or you predict the next 10 actions, right? Otherwise, what may happen is, which you will see in the example which I showed you, here the reason why the car is failing spectacularly is the moment it makes a mistake of going out of the road, it hasn't encountered such a situation in training data, which means it's again making a mistake. Then from that mistake, it again makes a mistake. So those mistakes simply compound. And like what is shown in this figure, it simply goes out of the trajectory. And once it is out of the trajectory, it doesn't know what to do anymore because that training data is not there. And you might want to take a guess, what was my training accuracy in this experiment? It's like 90%. It's like 87, 90%. So even that, not training accuracy, validation accuracy, even that level of validation accuracy is not enough because even then there is a 10% chance of making mistake and that mistake can compound. In action chunking, what we do is your model is learning to predict 10 actions at a time. And if the validation accuracy in action chunking transformer is really good, we can hope that because it is predicting 10 good actions, minor mistakes, because it's making predicting 10 continuous actions, in the next step, it will not make a minor mistake because you are looking at a longer horizon. In the training data, the road is curving after 2 actions. And in the training data, because the curve is already coming ahead of it in the training data, in the action chunking transformer, it already knows before even the curve is reached, somewhat, okay, in 10 actions, you will never go that much distance, but to some extent, you are like predicting slightly into the future. And in the training data also, you will have something like that. In the training data, when you drive, when you collect actions, you will pool 10 actions or 5 actions together, and you will train the model to predict all those 5 or all those 10 at once. And because of which the model is somewhat able to predict the future a little bit more. How do we choose the chunking size? So chunking size is, if the chunking size is too big, your inference will be extremely slow. So if you pick, for example, chunking size is 100, your trajectory could be smooth, but inference will be super slow. If the chunking size is like, let's say 1, there is no point in using action chunking transformer. So chunk size, typically what we use in robotics and in VLA, especially physical experiments, is between 5 to 10. In papers, I have seen people use 100 also. Maybe because they have a powerful inference engine available. But in typical cases, we just use, in these experiments, we will just use a chunk size of 5 or 10. We will work on real benchmark data sets like bench to drive or nav to sim, so that we can get real world experimental data. Yeah. So in future models, I do plan to use some real world data. But you know what, Akash, the problem with real world data is, look at where we are going to implement our real data. Our real data will be going to implement in the TurboPi car. The camera of the TurboPi is never going to see a road environment. It is always going to see your indoor of your house, or indoor of our office. It's never going to see same thing which an actual driving car is seeing. On the other hand, in SO101 kind of 6 degree of freedom robots, almost always all the tasks are like indoor on a table. There is a table on which bunch of things are set up. There are multiple cameras. So even if you collect data from internet, and if you try to build your own experimental setup, the training data and your experimental setup are not too different, right? But unless we are actually having a full scale driving car, and unless we are actually driving on the real road, or in a 3D simulated environment like Carla, which is very expensive to run, it's very difficult for us to use real training data and then try it on our TurboPi. So for the purpose of TurboPi, we will have to collect training data from scratch. And in fact, it is one of our goals to build one of the biggest collections of training data sets for such indoor small cars. All right. There is one question. Does it recompute at additional intervals or recompute based on the events? You mean in action chunking, Rahul? Are you asking with respect to action chunking? So in action chunking, what happens is this. There are different cases. In one case, let's say you are predicting, in each prediction, you are, let's say, predicting 5 chunks. Okay. You could make the next set of action chunking predictions after these 5 chunks or before itself. So let's say after three actions, you predict the next chunk. Then after these 1, 2, 3, 4, 5, 6. So by the time you reach here, you will have another 3 chunks, another 5 chunks. So now what happens is, look at the chunk number 1 and chunk number 2. And these are time step 0, 1, 2, 3, 4. Now this is 5, 6, 7, 8, 9, 10. For time step 1, 2, 3, these 3 chunks are unique. For time step 8, 9, 10, not 3 chunks, these 3 actions are unique. For 8, 9, 10, these 3 actions are unique. But for time step 3 and 4, there is an overlap. From chunk number 1, there are 2 actions. And from chunk number 2, there are 2 actions, which means you can average them. So you average this plus this divided by 2. That will be the action corresponding to time step 3. This plus this divided by 2 will be what corresponds to action number 4. Similarly, 5 is unique. Then these 2 will be added for step number 6. These 2 will be added for step number 7. So in action chunking transformer, if you predict the next chunk before fully executing the current set of chunks, you simply average the overlapping parts of the chunk. Now, in the example which we are doing today, we will not be doing this overlap. It will be simpler than that. Now, so in action chunk, essentially, this is what we do, right? At each point of time, we are predicting the future. And because of that, there is a smooth driving. And you will see that, like, if you go to this video, I'll share you this video link. If you go to this video, the very last experiment at timestamp 259 or timestamp around 3, it's actually action chunking transformer. And you will see that the driving is way smoother. So look at this. it's really not that much going outside of the road. It's pretty smooth. I mean, when I say pretty smooth, I mean compared to the rest of them. And I'll show you the one where it drives on the right. Look at this. It's pretty smooth. So I was so happy to get this outcome. All right. Now, let's discuss a few different architectures that I want to go through in these 9 experiments. So why does action chunking reduce compounding error? A quick question. I'm sure all of you know this. Basically, model has a temporal horizon over which it is making the prediction. In case if there is any mistake, if there is chunk overlap, as I showed you, the overlap averaging will take care of any mistakes. Then now let's go back to our discussion. Okay. So our discussion started around this. We have 2 cases. We have a curved road where driving happens just in one direction, where vision language action is not required. In forked road, there is left or right. Now, there is another case where in forked road, there is no vision language action is required. So I'll let me just write 2 situations for you. In curved road, so the following experiments are what we are going to do today. Not fully, but we'll discuss them. We'll do one experiment. So in curved road, we can just use vision only encoder, which is like a CNN. Okay. We could use ACT, action chunking transformer, without something called as conditional variational autoencoder. I will tell you what this is and why this is needed, but just bear with me for a moment. We will implement ACT with conditional variational autoencoder. So these 3 experiments we can do in curved road. Okay. There is no language. So in none of these experiments, there is language. No language. So these are not vision language action models. These are just vision action models. In forked road, because there are 2 options, can we have a vision only encoder in this case? In forked road? Is this something which we can have? I mean, ideally, we need some language, but there is nothing wrong in having vision only encoder, in the sense like, how would you have vision only encoder? Same vision only encoder which you used in curved road, you use here, except in half of your experiments, you drive to the left, half of your experiments, you drive to the right. But there is a problem with that. I'll tell you the problem, but technically, this is something which we can try as an experiment, right? So vision only encoder we can try. Another one is vision encoder plus language. So vision plus language encoder. So now this is VLA. This we can try. Second is ACT without conditional variational autoencoder. This we can try. So there is no language. So this has no language. This has no language. Fourth is we can try action chunking transformer with conditional variational autoencoder. And this has also no language. Now comes the 2 parts where there is language. ACT without conditional variational autoencoder, but plus language embedding. So this is technically a VLA. Last one, which is the most comprehensive one, ACT plus conditional variational autoencoder plus language. So this is the proper VLA, and this is the one that I'm showing here in the 9th experiment. So totally, if you look at it, 6 experiments are possible in forked road. 3 experiments are possible in curved road. In curved road, there is no language. In forked road, in half of the experiments, there are no language. So this one, and this one has no language. In the other half of the experiments, there is language. And that too, in those experiments where action chunking transformer is used, in half of the experiments, we don't have conditional variational autoencoder. In half of the experiments, we have conditional variational autoencoder. And I'll tell you why we need CVAE when it comes to the slide. But you can already imagine that if same number of experiments are recorded in every single one of these, this should ideally work the best. this should be the best, and this probably should be the worst, correct? Because here, just with vision, now the model has two options to pick. It can either go through the left and or go through the right. But how does the model know, right? So this should be ideally the worst, and this should be ideally the best. And we'll discuss that also. So first, let's go through the architectures, okay? So this is the architecture which we already discussed, the vision only part. So you have a camera image, 128 by 128 by 3. So here I'm writing the dimensions like this: batch followed by channel followed by space. So b comma 3 comma 128 comma 128, which passes through a 2D convolution followed by ReLU. So batch dimensions remains the same. Channels increase to 16. Number of actually, let me take a screenshot and so that I can annotate. So batch dimension remains the same. Spatial dimension shrinks to 64 by 64. Channel dimension increases. And by the time you pass through three convolutions, and the fourth one is average pooling, you will have just batch dimension followed by 64 dimensional like a vector. Then that you will pass through MLP, multi-layer perceptron, where 64 dimensions is projected to 64 itself or to 128, and then that is projected to 4 dimensions. So finally, you have batch dimension followed by 4-dimensional output. 4 dimensions are forward, backward, left, and right. So this is one that I already showed you. And here the output results for me when I ran the experiment. You can also run the experiment very easily. So to run the experiment, just go to this one, exp1vla.versal.app. Just click the training data. It will download the training data. Click the collab notebook. It will download the collab notebook. Today we'll be only going through one collab notebook for the ACT with conditional variation autoencoder with language, because that's the most comprehensive one. So we'll go through this collab notebook in detail, but the rest of the ones you can run on yourself, because it will take some time. The training is not that quick. Even with GPU, it takes time. But the validation accuracy which I got for these experiments were around 90%. So for this specific experiment, I thought it was like, yeah, around 90%, not exactly 90, but somewhere around that. Okay. Which made me feel like, okay, this might be a really good validation accuracy. However, when I try this in inference, so if I go to inference, if I click load bundle model, and if I go in autopilot mode, it's not that smooth. And the main reason for this is there is only vision included here. And there is no language conditioning. Plus there is it's just behavior cloning, like the expert's behavior is being cloned. And if I go to, I think, experiment number 4, it should be the same version, but on the forked road. So this is now the forked road with only vision encoder. So here I have mentioned vision encoder forked road. Okay. And here, if I click inference and load bundle model and then autopilot, you will see that it always takes one of these actions. I think in my experiments, it always takes right, and then sometimes it goes off road. But there is one confusion for me here. This is not the behavior that I was expecting. I was hoping that when training data was collected, the number of training data where the model goes into the left and number of training data where model goes into the right will be equal, right? And because of which, the car will just go and hit the tree in the middle. So I'll tell you why. So I'm sure you all know about regression, right? So in regression, let's say, and in essence, CNN is also almost like a non-linear regression. So when the car is at the starting, okay, so let's say this is the curved road to the left and this is the curved road to the right. When the car is at the starting, the input X is the same, but corresponding to the input X, there are two different actions possible. There are two different Y values possible. Okay, so let's say when X is this, let's say you have a data set like this. When X is equal to 1, then when X equal to 2, when X is equal to 3. Okay, then let's say your data points are like this. If this is how your data set looks like, and if let's say this is a linear regression, your regression plot curve will look something like this, correct? What if your data looked something like this? What if your data was like this? Where would your line stay? And what does this mean? For every possible input, there are two possible sets of actions, either these sets of actions or these sets of actions. For input 2, either these sets of actions or these sets of actions. So in this case, when we are performing regression, will the line be here? Will the line be here, or will it be somewhere in the middle? It will be somewhere in the middle. That's when the loss is minimized. If it is here, the loss due to the other set of actions are high. If it is here, the loss due to the other set of actions are high, which means the model will learn to predict something like an average. Now, you know what this means. What this means is, let's say x equal to 1 is the starting point, and these are the actions where the car goes to the left, and these are the actions where car goes to the right. Ideally, if the training data is equally balanced on both sides, the prediction would be such that the car will neither go to the left nor go to the right. It will directly go and hit the tree. You can very easily test this. You yourself run one set of experiment, 1 or 2 on the left and 1 or 2 on the right, and just use that training data and train the model and see where the car goes. Okay. But this problem is called as the collapse of the modes, in the sense that the data has two modes. In one mode, the probability shows that the car is on the left. In another, the probability shows the car is on the right. And instead of learning that the data set has two modes, there is collapse of two modes, in the sense both of this will be averaged by the model, which is not a good thing. I'll show you one more slide regarding that. So this is one reason why we have to introduce conditional variational autoencoder when we get to ACT. We have not talked about ACT, action chunking transformer, yet, but just understand this. This is the reason why in my experiment number 4, I was expecting my car to directly go and hit the tree. But my suspicion is, because it's not going and hitting the tree, it's going always on the right. My thinking is, when we collected the training data, maybe when I collected the training data, I made sure that it is equal number on the left and equal number on the right. Maybe it might have happened that when people recorded it, they might have predominantly recorded a bit more on the right. And because of it, it has a bias towards the right. But otherwise, if you record your own training data, ideally, if it is equal, it may go and hit the tree. It has happened before for me. Okay. It's just a theoretical artifact of the model not being able to capture the fact that there are two possible actions for the same input. And in robotics, this is a big deal, because think about it. When a robot is going and picking up, if you are going and picking up something like your phone or something, you can go from point A to your phone through many different trajectories, right? It's not like you always do the same thing. For going from point A to point B, there are many different possibilities. And robot should ideally learn that fact. It should not just learn an average trajectory. Now, in the forked road case, only one difference which I had made to the model was I had one additional convolution layer. So I had, instead of 3 convolutions, I had one fourth convolution. I just thought of doing this because I thought the number of parameters that this model has should be slightly greater than the number of parameters which the curved road has. Because in curved road, there is no decision to make. The only decision is just to drive. In forked road, you have one more decision to make, whether to drive on the left or whether to drive on the right. But I'm not saying this will add any extra speciality or anything, but this is what I tried. Okay. And it is surprisingly working. I was expecting it to not work because of the reason of this mode collapse, but it is working maybe because of the bias in the training data. I have to check that. But I urge you to try this experiment. And here also, I got a validation accuracy like 91.7%, which doesn't mean much in inference. In inference, each mistakes can compound. So you have to, the difference between 90% and 95% is huge in self-driving. Then now comes the idea of action chunking transformer. Okay. So in the case of convolutional neural network, what we did was we had 64 by 64 by, what was it? 16 or no, 16 by 16 by 64. So we had batch dimension. Then we had 16, 64, 64. Okay. This is what we had. Then what we did is we converted this into B, 64, 16, 16 in the last layer. And then what we did is we did global average pooling of these two to convert this into B, 64. This is what we did. Now here you understand the problem. The spatial information which is distributed in a 2D fashion. If there are 16 by 16 pixels, it will look something like this. So we have a spatial information distributed in 2D. This 16 by 16 is distributed like this. We are collapsing all of that spatial information into one single number. That was the problem. Instead, what we should ideally do is some sort of tokenization where this 16 by 16 is converted into certain number of tokens. And now those tokens, through those tokens, we can construct self-attention. And that self-attention will help us pay attention between, let's say, this part of the image and this part of the image, which is called as long-range dependency, meaning pixels on two different far ends of the image should pay attention to each other. Just like this. In large language models, the teacher who was teaching a difficult concept to the students smiled. Now, this is a very big deal for a large language model. You know why? Because here students and smiled are appearing close to each other. Teacher and smiled are appearing far from each other. Yet the attention weights between the token corresponding to teacher and token corresponding to smile should be highest. The reason is teacher is the one who smiled. It's not students. But typically, because of if models do not have long range dependency, it will not be able to learn that these two tokens have very high dependency. It may learn that by mistake. Students and smile, they are the one who are correlated. But large language model, because of its self-attention, tokens, even though physically they are far apart or geometrically they are far apart, you can construct large attention scores between them. And that same concept is also needed in images. Because let's say you have a self-driving car where there is a green signal. Okay, in this patch of pixels, there is a green signal. But on the road, let's say there is a guy who is crossing here. So car should not just pay attention to this green signal and take forward. It should also take into attention these set of pixels, which are far away. So now these groups of pixels are far away. But those two are highly correlated. Why? Because if the car takes forward, because of it seeing green signal, this guy might have crossed and reached the half of the road and you might just run him over, right? So you don't want that to happen. So you need long range dependency between tokens in visual tokens also. So you need some sort of tokenization followed by self-attention. So what we are doing here is, instead of collapsing 64,8,8 or something like that into 64,1, so instead of collapsing the 8 rows and 8 columns into one single number, because 8 by 8 is 64, we will convert those 8 by 8 into, instead of being one number, we will convert it into 64 visual tokens. So now you have 64 tokens, each whose dimension is, so we have now 64 tokens, each whose dimension is 64. So 64 dimensional tokens, and we have 64 such tokens. And I'll just show you one picture. Something like this. So if you have an 8 by 8 grid of patches, this is token number 0. This is token number 63. And self-attention should ensure that the tokens are all having high attention between each other. And self-attention formula is query multiplied by transpose of key divided by square root of dimensionality of queries, softmax of that multiplied by values. We'll discuss this in a little bit of detail, how exactly to get an intuition about this formula. I'm expecting you to have already gone through the transformer-based lectures which I had posted. But this is what we are going to do now. Instead of converting the convolution features into just a one number through global average pooling, we will convert them into tokens. Tokens will be passed through a transformer encoder so that self-attention is applied. And then we will see how to use decoder with language to produce the appropriate actions. Okay, so this is what we are going to do next. Okay, so let me spend a little bit of time on this attention mechanism, just to make sure that you guys know what this is about. So let's say you have these tokens. The cat sat on the mat. And let's say one word is equal to one token. So these are 6 words. So you have 6 tokens. Okay. So the cat sat on the mat. Now, when we convert these tokens into the query key value space, and let's say these are called X, this is all X. How do you convert X into query? You multiply it with the query weight matrix. So X multiplied by WQ, or depending on the dimension, WQ multiplied by X will result in query. Similarly, the same X you can multiply with weight matrix for key. So K multiplied by X is key, and WV multiplied by X is value. So now you have query, key, and value vectors. So how many such query vectors will be there in this case? If this is my input, how many query vectors are there? Basically, every token we have to convert to query, every token we have to convert to key and value. So if there are 6 tokens, there are 6 query vectors, there are 6 key vectors, and 6 value vectors. Okay. Now, what we want to do is, at the end of the day, input tokens we want to convert into context vectors. So 6 input tokens we want to convert to 6 context vectors. This is our ultimate goal. Okay. And what is a context vector? Context vector in plain English, you can write it as attention weighted sum of value vectors. In simple terms, this is what the final context vector is. And I will show you how this is coming mathematically. So basically, at the end of the day, you are doing some sort of weighted sum or weighted average of value vectors to produce context vectors. So let's keep the value aside. Now the thought is, okay, you are doing some sort of addition of value vectors, and we are having some weighted sum. So what are these weights? These weights are attention weights. So now the cat sat on the mat we have, right? So the cat sat on, actually, let me draw like a table, that'll be easier. So the cat sat on the mat. And here also the cat sat on the mat. In the normal convention, can you tell me these are what? Tokens converted to query or key? These sets. These are tokens. This is not direct tokens, by the way. These are query tokens. So this is the query corresponding to this is the query corresponding to cat, query corresponding to sat. Okay. And similarly, this is key corresponding to the key corresponding to cat, key corresponding to sat, etc. Now, what we are doing is, in typical transformer architecture, what we say is, we try to predict the next token, which means if query is it does not have access to cat sat on the mat. It only has access to tokens until that point, which means you say the attention weight between the and this the is simply 1, and there is no attention paid from the to cat, the to sat, the to on the mat. All of these will be zeros. But when the query is cat, it has access to the and cat. It does not have access to sat on the mat. So these are zeros. But these two numbers will be a probability distribution. So let's say this is 0.6 and this is 0.4. So these two should sum up to 1, because now it says cat will pay 60% attention to the and 40% attention to cat itself. And sat will not be looking at on the mat because those tokens are coming afterwards. So this will be zeros. This will be 0. this will be 0. And sum of this will be, let's say, 0.3, 0.6, and 0.1. These 3 should sum up to 1. These 4 should sum up to 1. These 5 should sum up to 1. And these 6 should sum up to 1. And you know what this is? This is query dot key transpose divided by square root of D applied with softmax. Because softmax will ensure that this entire row will always sum up to 1. So if you look at any one row, the sum of this one row will be 1. If you look at this row, sum will be 1. If you look at this row, the sum will be 1. So softmax probability distribution is applied these row wise. That's how you get these numbers. Now what you do is, now you have value vectors. So value vectors are what? The cat sat on the mat. So the dimension of this is 6 by 6. The dimension of this is 6 by 1. Okay, so this is value vectors. Now what you do is, your context vector number 1 will be 1, and let's say the value of these value vectors are some random numbers. I don't want to call it, maybe V1, V2, V3, V4, V5, V6. These are all vectors, by the way. Okay, these are not individual numbers. And when I say 6 by 1, there are 6 vectors of maybe dimensionality is, let's say, 768 dimensions. So this has 768 dimensions. Each of them is a vector. Like that, there are six vectors. Okay. Now what will happen is, what is the context vector corresponding to first token? It will be 1 multiplied by V1 vector. So first context vector will be V1 multiplied by 1. Second context vector will be 0.6 multiplied by V1 plus 0.4 multiplied by V2. So 0.6 V1 plus 0.4 V2. And third will be 0.3 V1 plus 0.6 V2 plus 0.1 V3. Now look at this. This is context vector number 1. This is context vector number 2. Next is context vector number 3. Like that, the last one will be simply, let's call this as W61, W62, W63, W64, etc. The last one will be W61 times V1 plus W62 times V2 and so on. And last one will be W66 times V6. This will be the context vector number 6. Now look at this. Attention weighted sum of value vectors. Where is the sum of value vectors? V1 plus V2 plus etc. up to V6. That is the sum of value vectors. But it is attention weighted. You are multiplying, you are not adding the value vectors directly. You are weighing it based on attention score. So W61 is multiplied with V1. W62 is multiplied with V2. W66 is multiplied with V6. So context vector is equal to attention weighted sum of value vectors. Okay. And this single thing is represented by this formula, query.key transpose divided by square root of dimensionality of query space, softmax of this multiplied by V. So this is ultimately, so when people say attention of query, comma, key, comma, value, ideally I should say context vectors is equal to attention function of query key value, which is equal to softmax of query.key transpose divided by square root of D multiplied by V. Okay. Now, I hope you understand now the origin of query key and value. The origin of query key and value are all from the original 6 tokens. So you had 6 tokens corresponding to your 6 words. Those tokens resulted in 6 query key value vectors. Oh, one more thing, just to make it clear. This value, the dimension of this value vector, this is 768. Let's say this is 768. This is 768. So the final dimensionality of this context vector will also be 768 because you are just adding up 6 vectors with a weighted sum. Okay. So depending on, and this value vector dimension should be ideally be at the end of the day, after multi-head attention, it will be same as your, in most cases, same as your input tokens. If input tokens are 768 dimension. But anyways, so this is what happens in the encoder, correct? This is what happens in the encoder in pure text. Here it is not pure text. So we have to discuss a few more things. Now, similarly, if I convert my image into tokens, so how does image become tokens? So I said my image became B, 64, 16, 16. So what does it look like? 16 by 16 will look something like this. And I have 64 such items. Okay, so I have 16 by 16. Like that, I have 64 items. And 16 by 16 means I will have 16 such vision tokens here. Okay. Now, what will happen is if I have 16 by 16, or let me just make it simple. This is 8 by 8. That's easier. 8 by 8. How many tokens are there? My X is equal to how many tokens? The input. Is it 8? How many tokens do I have? I have 8 times 8. That many tokens, right? I have 64 tokens. What is the dimensionality of the tokens? X dimensionality. It is also 64. Now let me ask you one more thing. If I change this to 128, what changes? Is X changing or X dimensionality changing? X dimensionality changes. The channel dimension will become the dimensionality of the embedding space. So this, instead of 64, it will become 128. Okay. Now just tell me, if I have 64 tokens, what will be the shape of my attention weights matrix? My attention weights matrix will be like what type of square? What dimensional square? I will have 64. Think about this. If I have 64 tokens, if they are converted to query, I will have 64 as query. I will have 64 as key. I'll have 64 as value, correct? Which means my query dot key transpose, that attention weights matrix, will be 64 by 64. That's the reason why attention complexity is told to be scaling with the square of number of tokens, right? And in image, it scales with quadratically scales with the image size. So look at this. The size here is 8. 8 square is 64. 8 cube is this is what? 8 times. So number of attention weights that you need to calculate is 64 times 64, which is 8 square times 8 square, which is 8 raised to 4. So if image size is, let's say, one side of the image is 8, 8 will become 8 raised to 4. So this much complexity increases, attention calculation complexity increases. All right. But anyways, that's just a side note. Now my question is, where are these queries coming from? And where are these keys coming from? And if you have 64 values, where are they coming from? Where is the origin of your query, origin of your key, and origin of your value? It all comes from the image tokens, correct? Because here you are paying self-attention to image, right? So these are your image tokens. This is image token number 0. This is image token number 0, but it's second dimension, it's third dimension, it's fourth dimension, it's next dimension. So this is basically, these items are your image token number 0. Similarly, the last one, this is image token number 63. This is the next dimension of image token number 63. This is the 63rd image token, so on. Now, these image tokens are projected into query key value space. Now, can you tell me, do you want masking here, masked self-attention? So when query.key transpose is constructed, do you want these to be zeros? Why not? For those of you who are saying no, why not? The reason is we are not predicting the next token. We are not predicting the next image. We want to make sense of all the different tokens that are there in the image. It's not like here we are trying to create a new token. Unlike in language, we are trying to create a new token. So peeping into the future is not allowed. So here we don't need masked self-attention. We just need self-attention. Okay, so just pay attention to that also. So now coming back to what we are now going to do. Okay, so just understand this much. Image tokens are now converted into context vectors. And for context vectors, we will apply self-attention. And in application of the self-attention, we will not be applying masking. It's not needed, unlike language. Okay, just a quick question. In ACT we are yet to discuss, but we'll come to that. In ACT's encoder self-attention, where do QKV come from? Yes, feel free to answer. It comes from, all come from spatial tokens, same source. Okay, so B. Now, let's look at decoder. I'm yet to show you the full architecture. So let's first draw the full architecture. Action, chunking, transformer. So in ACT, what is the input? 128, 128, 3, some image like this. What should be the output? Let's say chunk size is equal to 3 or 5. What will be the dimensionality of the output in our case? It will be 4, 5, right? Each action is basically 4 items, 4 dimensional. And like that, I need 5 actions, right? So if batch dimension is also there, B, 4, 5. This will be the output. And here also, if batch dimension is there, B, 128, 128, 3, output will be this, correct? Now, we told that input, which is B, 128, 128, 3. I think the way I am writing in the figures is B, 3, 128, 128, if I'm not wrong. So just let me keep it consistent. After convolution, after 2D convolution operations, multiple of them, conv 2D operations, this will become B, 16, or rather 64, 8, 8. Now, what do? We convert this into tokens. So how many tokens do we have? We have a batch size of B. We have 64 tokens. And dimensionality of each token is also 64. Okay, so this part is tokenization. Now, after tokenization, we can, what is typically done in transformer after tokenization? To tokens, you add something, right? You can add a position embedding. So yeah, of course, encoding. But at the end of the day, position embedding is added. So that this position information is there in the tokens. And then finally, the tokens, the encoded tokens are sent into a transformer encoder. In which, so let's say it is coming like this. There will be layer normalization. Okay, first let's say multi-layer, multi-head attention, layer normalization. Then there will be residual connection. Then there will be multi-layer perceptron, layer normalization, another residual going around this. And then finally, what comes out of this will be context vectors. And if it is like a transformer architecture with multiple heads, multi-head attention will have multiple heads like this in parallel. In our case, the number of heads that we have defined is 2. And if transformer has multiple transformer blocks in series, same thing. This same thing will repeat n number of times like this. Right? So this is the transformer architecture. This is the same encoder that we are using in this case. Multi-head attention followed by multi-layer perceptron. So the dimensionality of my embedding space is 64 dimensional. And if multi-head attention has 2 attention heads, this is to just check your knowledge. Let's say this is dimensionality of my embedding. What is the dimensionality of my query? Query key value space. Each attention head will take care of 64 by 2, which is 32 dimensional. So the query in attention head number 1 will be 32 dimensional. In head number 2, it will be 32 dimensional, and so on. Okay. And layer normalization, there are different types of layer normalization. Pre-layer normalization is there, post is also there. So it depends on the architecture. This can be before or this can be after, but there will be a residual connection going around the MHA. There will be a residual connection going around the MLP. This for better back propagation of gradients during the training. In multi-layer perceptron, similarly, what happens is my input dimensionality is 64. In the architecture which I am defining, the hidden dimensionality is a multiple of 2. So 64 multiplied by 2, 128. And then it is projected back into 64. So this is the typical multi-layer perceptron architecture used in transformers. And the number of transformer heads, if I'm not wrong, in the code, I'm using only one transformer head. So the second transformer head is not there. Okay. So by the time the tokens, these 64 tokens reach here, you will have B, 64, 64. So 64 dimensional tokens. Like that, I have 64 tokens and batch size is B. These will not be just tokens anymore. These will be context vectors. Okay. So these are my context vectors now. So now in the action chunking transformer, this is only one part where we are using a transformer encoder to encode the context vectors, right? But now to produce, we need to finally produce an output, right? What do we need for producing an output? We need a decoder. So we need a transformer decoder. So decoder, let me draw it over here. So let's say multi-head self-attention. In this case, I'm not sure if it is pre or post normalization. Let me check the normal transformer architecture, because I have been doing both recently. Okay, so it's post normalization. So let's say followed by layer normalization, then followed by multi-head cross attention, followed by multi-layer perceptron. And there will be one layer normalization after this. There will be one residual connection going, no, not around this. Around this, there will be one residual connection. Around this, there will be one residual connection. Now, I'll show you a better diagram. Pardon my handwriting. Now, this is the input. This is the output. Now, tell me what goes into the input of this decoder. And I have one more thing coming here. So, input 1, input 2. Now, just tell me what is the input 1? I'm just trying to understand your knowledge. What would be input 1 if I have a transformer decoder like this? Input 1 will be the action tokens which we initialize. So how many action tokens we need? We need 5 action tokens. So 1, 2, 3, 4, 5. So we will need 5 action tokens initialized. Okay. So this will be the input. Then there will be a self-attention, multi-head self-attention applied between these 5 action tokens. Then it reaches the multi-head cross-attention part. In cross-attention, okay, now first of all, let me ask you, here, where is query coming from? Where is key coming from? Where is value coming from in this cross-attention? And by the way, what is input 2? What is input 2 and what is the query key value in this cross-attention? Input 2 is clear. Whatever context vector you get from the encoder, that is primarily what you're passing into the, so this context vector. So this is the output from encoder will be passed into the into this, right? There is one thing missing, but I'll come to that. So this is coming into the input. So now tell me, in this multi-head cross attention, query is coming. Where is the origin of the query? Where is the origin of the key? And where is the origin of the value? Query will be the number of query tokens. Okay, think about this. The number of query tokens will be same as the number of tokens you need at the output. Number of tokens you need at the output here is you need 5 action tokens, each of dimensionality 4, because forward, left, right, back. 4 actions are there. So each of these are now like this, 4-dimensional. Like this, 4-dimensional. I need 5 such tokens here. And at the output also, I need 5. Because my chunk size is 5 in the ACT. If it is 10, I will need 10 like this. Which means query will be projection of whatever comes out of here into query space. So Q will be originating from ultimately these tokens. Key and value will be originating from the output of the encoder. So this will be coming from action tokens. Key will be from encoder output, encoder context vector output, CV for context vector, okay. Value is also from encoder context vector output. Basically, how do you get that? These context vectors you multiply with the query key weights matrix, so WK matrix, to get the keys and values. And why is it now called cross attention? It's called cross attention because let's say the output from the encoder had how many tokens? You had 64-dimensional tokens, right? Okay, by the way, this input may be at the starting, it may not be 4-dimensional, that we can do at the end. The input may be starting at 64 dimension, that we can clarify later. It can be anything that we can finally project into 64 or 4 dimensions. So let's say this is starting as 64-dimensional vectors. Then what we have now is, I have 5 action tokens, action token number 1, number 2, 3, 4, and 5. Okay. Now I will have a matrix like this. Or not this. I will have a matrix like this, where I have 5 rows and how many columns? I will have 64 columns. These 5 rows correspond to 5 action queries. And these 64 correspond to 64 context vectors coming from the transformer encoder output. So now my query.key transpose will be essentially 5 times 64. This will be the dimensionality. It won't be square. Value will be of what dimension? What will be the dimension of my value vectors? How many value vectors are there? The value vectors are originating from the context vectors coming from the output of the transformer encoder. So there will be 64 value vectors. Each value vector will be of dimensionality, whatever the dimensionality of this embedding space. So I think in this case, the embedding space has a dimensionality of 64 only. So value vectors will be 64 by 64. Query will be 5 by 64. Key will be also 64 by 64. Because I have 64 keys, each of which dimensionality is 64. Now, how do you get the context vector, the output from here? The output after multi-head cross attention, how do I get? I get like this. This guy is multiplied with this guy, then plus this multiplied by this, plus this multiplied by this, plus this multiplied by this, plus this multiplied by this. So if I call this as W11, W12, etc. So my first context vector CV1 will be W11 multiplied by, what should I call this? K, I can call it as something, but W11 multiplied with Q dot K transpose, where Q is 1 and K is 1, multiplied by Q dot K transpose, where Q is 1 and K is 1, something like this, multiplied by, or actually, you know what? Why do I need this if I had W? So W11 multiplied by V1, then plus W12 multiplied by V2 plus etc. W164, 1 comma 64 multiplied by V64. So this will be context vector number 1. Like that, how many context vectors do I have? How many context vectors do I have? No, please pay attention. How many context vectors do I have? Think about it. It's same as the number of rows, right? This one row is getting multiplied by this one thing, this value, not one thing, these value vectors. Like that, I have 5 rows. So I have 5 context vectors. The last one will be W51 multiplied by V1 plus etc. W564 multiplied by V64. This will be the context vector number 5. And why do we have 5 context vectors? Because we have 5 action queries. Because those queries we need to convert into context vectors, finally, which can be used for producing actions. We have 5 chunks. If this was 10, I would have had 10 such context vectors. The dimensionality of each of them by default will be same as the dimensionality of the embedding space. So this will be 64 dimensional. Each of these will be 64 dimensional context vectors. Now what we can do is, if what comes out of here is 64 dimensional, okay, so let's say each of these are 64 dimensions, we can use one projection layer to project the 64 dimensional into maybe we can have an intermediate layer of 64 or 128, and finally we can project that into 4. Just like what we had in CNN. In CNN also, same thing we had, if you remember. Look at this. We had an action head which projected 64 into 64 only. 64 was projected into 64. Then it was projected into 4. Same thing we can have. And that's how we can get the action tokens. Okay. So now if I were to show this to you in a little bit cleaner way, let me just show you the diagram. Okay, so this is the query, by the way. So I have 5 queries. These queries are all cross attending to 64 tokens, spatial tokens. This is very straightforward. Then this I already told you. Yes, I think this is vision only ACT, right? Yeah, exactly. So now this is the simple architecture. I have the simulator, a camera image 128 by 128 by 3, which passes through CNN, which produces 64 tokens. So the tokenizer will convert it into an embedding space, and position embedding will be added. So that is this. Let me just bring back the annotator. So this is tokenization. This is addition of position embedding. Following that, transformer encoder. I have only one layer, 2 attention heads. In each head, it will take care of 32 dimensions. Then feed forward network dimension simply means in the multi-layer perceptron in the transformer encoder, there is a hidden layer. That hidden layer's dimension will be 2x the dimensionality of the embedding space. So embedding space has a dimensionality of 64. So the hidden layer will be 128. So this is self-attention, which takes care of attending to all the tokens, all the 64 tokens in the spatial tokens. Then we have transformer decoder, into which one of the inputs. So this is now the input number 1. Let me just reduce the size of this pen. Yeah, so this is now the input number 1. The 5 action queries. There are 5 of them, each of them 64 dimensional. They will first undergo self-attention. Then it will undergo cross-attention with these 64 context vectors coming out of the transformer encoder. And the result will be 5, 64. Why 5, 64? You will have 5 action queries, each of which are converted to context vectors of 64 dimensions. So now each of them will be projected using an action head into another 64 dimensional layer. From there, it will be projected into another 4 dimensional layer. So now at the output here, what will we be having? We will have 5, 4. 5 action chunks, 5 actions, each with dimensionality 4. So each with dimensionality 4 meaning forward, backward, left, right. This is the action number 1. Then in the next time step, forward, backward, left, right, and so on. Okay. So this is a very simple ACT, action chunking transformer, with 2 important things missing. What are the 2 important things missing here based on our discussion so far? Okay, what is one important thing that is missing here? Language is missing. We have not added language. Second thing is conditional variational autoencoder. That's also missing. So we need to discuss that now. So far, so good, right? So we are having action chunking transformer in which there is a transformer encoder, transformer decoder, produces 5 action chunks, each of which are dimensions 4. But before all of this, to convert the visual into tokens or into features, we are using CNN. So this is where everything in computer vision is coming into picture. CNN, then similar to vision transformer, here is tokenization plus position addition, transformer encoder without any masking, transformer decoder where cross attention is there. Finally, a projection layer for projecting the actions from 64 dimensions into 4 dimensions. Very simple architecture. The code, I'm not going to show the code for this because when I show the code for the experiment number 9, which is the most extensive, you will naturally feel very easy about this. Code, you have it in the corresponding notebook. I'll be posting that. Now let's think about conditional variational autoencoder. Okay, for multimodal behavior. Basically, we have 2 modes. Okay, there is a question. Let's see. For intuition purposes, are there specific application types or ACT is indeed useful versus application where it has certain disadvantage? Plus, for application where ACT is useful, what are the key considerations to select the number of chunks? Yeah. So this will all come down to how fast can you perform inference. Are you okay with your robot moving super slowly, but it should be very precise? Or do you want it to perform certain action at a certain speed? In self-driving car, you definitely need fast inference, right? You don't want it to move like a very one step at a time. So in that case, you want a balance between action chunks for smoothing, but at the same time, you don't want too many action chunks. If you have too many action chunks, inference will be slow because you need to produce that many tokens. So at the end of the day, it will depend on how fast your application inference should be and how good of or how powerful of a inference engine do you have. To give you an example, till 2 or 3 weeks back, we did not have a powerful Mac Mini for inference. So we were doing inference on our own MacBook Pro, which is okay. I mean, but it's not that powerful. Now we have a powerful Mac Mini, which took us 2 or 3 weeks to even get it shipped here. So now we are able to run inference much faster, meaning our action chunk size can increase now. It can still give us similar speed as that of what we could achieve earlier. I think this decision is coming down to few such factors like how powerful is your inference engine, and how fast do you want the next set of actions predicted. If it's your local computer, which might be very slow, you might want to simply decrease the number of tokens, decrease the size of the chunk that you're predicting. So this is the problem which I discussed with you earlier. Like if you don't have a conditional variational autoencoder, which I'll discuss what will happen is you have 2 modes here. In one mode, your car is driving to the left and one mode car is driving to the right. And this I'm talking about in the case where language also is not there. So language, if language is also absent, meaning always drive to the left or always drive to the right, that decision, that language intent is missing, then for the same input, you have 2 types of outputs. But if language intent is present, then the input is different, because even if the car is present at that junction, the language input that is added to that image tokens are different, which means that inherently the input is different. But if language is missing, inherently the input is the same, because the car is staying here. It sees the same thing in the training data, but it has to take one action. So what typically happens is if your training data is well balanced, if there is no language and if there is no variational autoencoder, car will simply go to the straight, for the same reason for the regression example what we discussed earlier. So what we really need is from the training data, somehow the model should learn there are actually 2 distinct set of actions or 2 modalities, 2 modes are there for the actions. So the model should somehow know about that. This is where variational autoencoder is coming into the picture. So there is a question, if a stack is being scaled from low performance to a high, one can modify the chunk size. Yes, as far as I have experienced so far, yes. So even we literally did that. The moment we had a powerful Mac Mini, we could just run it for longer inference, which was taking us so long. So earlier our robot was moving like complete jerky motion, but now it's moving very fast and very smooth for the same chunk size. If we increase the chunk size, we could achieve the same speed as before. But now, since our chunk size is better, our prediction will be better. The motion of the robot will be smooth. It will not take sudden movements. So in all cases, what I have seen is if your architecture is not flexible, if you want to keep the architecture, if you can somehow have a high performance inference engine, you can go with a higher chunk size. From our robotic experiments so far, chunk size typically is in the range of like 5 to 20. From what I have seen in papers, it can be 100 or even 200. But I have never been able to run 100 chunk size very smoothly for my applications yet. Maybe it will in the future. So we need variational autoencoder for this purpose. Now, what exactly is, by the way, variational autoencoder? We need to discuss that very briefly. Variational autoencoder simply does the following. You have a bunch of input data. Let's say your data is, let's say, a bunch of actions. So when you are recording your car driving, you have corresponding actions, right? So ground truth actions. Ground truth actions. Now you have a set of actions, let's say an action chunk size of 5. So you have, let's say, 5 actions, each of which are embedded in a 64-dimensional space or something, or maybe 4-dimensional. That depends on what we want. What is done in variational autoencoder is you project this into a, you try to project this into a space, into a latent space. This is a latent space. Maybe the dimensionality of the latent space is a bit low. It's maybe 16-dimensional space. I'm just drawing 2 dimensions here. Okay. Now, in this projection, what you are trying to do is you are forcing the distribution of these data. And like this, there are many actions, right? Let's say you have 100 actions in your training. These 100 actions, you are trying to distribute in the latent space such that the mean is 0 and standard deviation is 1. So these 100 dots will be somewhere over here. Okay. These are dots. Okay. It looks like lines, but I have drawn dots. These 100 dots will be somewhere around mean equal to 0 and standard deviation equal to 1. Now, what will happen? How will this data, how may this data look like if, let's say, I am encoding using an encoder, using variational autoencoder, a data set which has, let's say, 10 modes. For example, MNIST data set has 0 letters, digits 0 to 9. So I have 10 different inputs. So how will that look like in this particular data set? Because this can involve 1, 2, 3, up to 10 or 0 to 9. So in this, how it may look like? Will it be equally distributed everywhere? Or will it be like something like there is one region where in this region, there is a concentration of digits corresponding to 0. There is another region where digits corresponding to 1 is there. There is another region where digits corresponding to 2 and so on. So such that there are different lobes or different regions within this mu equal to 0, sigma equal to 1 space where the data points corresponding to my large number of MNIST images are residing. It's more like this in the sense, if you plot your latent space in 2 dimensions, you will see that, and when you are plotting, you will have different colors, right? You will see that there are a lot of black dots over here. In another case, let's say you have red dots corresponding to digit number 6. You will see that there are a lot of red dots here. There will be overlap, of course, but you will see that in the latent space, this region in general corresponding to digit number 6. Then this region is corresponding to digit number 3. Similarly, in our self-driving car, okay, in the forked road map, if we were to construct a latent space like this, what will happen is we will construct a data points in the latent space. Let's say, for example, it's 2-dimensional for simplicity, a 2-dimensional latent space. Mu is equal to 0. Standard deviation is 1. The points may get arranged in such a way that it will look something like this. Now, can you tell me I'm not saying it is exactly how it looks like. I'm just giving an example. Now, can you tell me what these black dots correspond to and what these red dots correspond to? The black dots may correspond to you driving on the right, the actions when you drive on the right. Red dots may correspond to the actions where you are driving on the left. Okay. Now, when you are actually performing the inference, what you do is, in inference, what you do is you start with mean equal to 0, but sometimes you can also sample randomly from this space where mu equal to 0, sigma equal to 1. So what you're essentially doing is, in variational autoencoder, you are trying to map your input actions into a probability distribution like a Gaussian distribution whose mu is 0 and sigma is equal to 1. And this is done through something called as KL divergence. So KL divergence measures how much one distribution is close to or different from another distribution. For example, let's say I have a perfect Gaussian distribution like this, and my data distribution from my input data looks, let's say, something like this. So now essentially this is one distribution. This red color is another distribution. Now I can compare how this distribution is similar to or different from this distribution, which is very different from individually comparing. So I can compare this black dot with the corresponding red dot, which is over here. I can compare this black dot with the corresponding red dot, and I could construct a mean squared error saying this minus this the whole square plus this minus this the whole square plus this minus this the whole square. That is a mean squared error. There we are not comparing the distributions. There we are comparing the values. But comparing the distribution is slightly different. So there is a formula for KL divergence, which looks like, not this. I want the formula. Actually, I can show it in the code. That'll be easier. So this is the formula. It's basically minus 1 by 2 multiplied by sigma 1 plus logarithm of variance log of sigma square minus mu times mu raised to 2 minus logarithm of exponent of logarithm of variance, which is variance only, minus sigma square. Then I think this whole thing should be divided by the total number of items. So 1 by n, where I equal to 1 to n, something like this. So you can have a formula like this, which will help you with calculating the logarithm of calculating with the KL divergence between two distribution, where I equal to 1 to n means you are looking at one more thing, log var of dot exponent. Okay, I think if I pick a proper formula, that is better. KL divergence formula. I mean, this is the formula, this one, but instead of this formula, it's better to see that in, yeah, something like this. So this is the final KL divergence formula between two distributions of mu1 and sigma1. So one distribution has a mean of mu1 and standard deviation of sigma1. Another one has mu2 and sigma2. In our case, we don't have, for training data, there is no mu1 and sigma1. We just have data points. But for prediction, what we are trying to do is we are trying to map the input data points into a distribution whose mu is 0 and sigma is equal to 1. So after substituting mu equal to 0 and sigma equal to 1, you will get a formula which looks somewhat like what I showed you, this one. Okay, so there is actually this is corresponding to mu1 square. But since mu1 is, no, not mu1 square, this is corresponding to sigma1 square. But since sigma1 square is 1, this became 1. But there will also be like a mu1 square also is there in this expression. But since our target distribution has mu equal to 0, that term is not present in this. Okay. So the target distribution has sigma whose value is 1, mu whose value is 0. That's the reason why you only see mu and sigma. You don't see mu1, sigma 1, mu2, sigma 2. You don't see that. The reason why you don't see that is because the value of sigma, mu1 and sigma 1 is already substituted into this formula. But basically, this is how you compare your training data distribution to a target distribution who is a Gaussian, whose mean is 0 and standard deviation is 1. That's the reason why we are not constructing a mean squared error loss, something like, predicted value of y minus actual value of y sample from a Gaussian, squaring this and then doing 1 by n. We are not doing this because this is mean squared error. This is not KL divergence. Now I'll tell you where all of this come into picture in the vision language action transformer architecture. So what we do is we try to use this conditional variational autoencoder. So let me just show you this image. So if CVAE was not present, this whole block will be absent. This whole block will be absent. But now this block is there. So what it does is you have an action chunk. This action chunk of 5 actions of 4 dimensions is now projected into a space of dimension 16. The projection is done in such a way that the encoder part of variational autoencoder, which will be just like a multi-layer perceptron, it will try to predict 2 outputs. It will try to predict a mu and it will try to predict a logarithm of variance. Why logarithm of variance and why not variance directly? The reason is variance is a positive number. Variance is sigma square, right? It's always a positive number. But logarithm of variance can be negative also. So instead of predicting variance, if we try to predict logarithm of variance, it's very natural for a neural network, because when a neural network makes a prediction, we cannot force it to just produce positive numbers. It can produce negative also. So for the purposes of gradient descent, etc., it's better to predict logarithm of variance. And if we need variance, we can just take an exponent of this. So what the encoder part of the variational autoencoder, which is just like a multi-layer perceptron, what it will try to do is, it will try to make a projection from this 4 dimensions into 16-dimensional space. And it will try to predict 2 numbers, mu and variance. Now we have to penalize the encoder for predicting mu far away from 0. And we have to penalize the encoder for predicting logarithm of variance far away from, variance far away from 1. Right? So that penalty we need to introduce somewhere in the loss function. I will show you that. Then what we do is, now this is the encoder part of the variational encoder. Now we need to sample something from this distribution of mu and sigma. So what is done is, if we have a distribution of mu and sigma, what we do is, if the encoder part of variational encoder predicts a mu, and if it predicts a sigma, what we do is, using a random number generator, we'll generate a parameter called epsilon. Now we say that the new parameter which this variational autoencoder predicts in the latent space Z is equal to mu plus epsilon sigma. So mu is predicted by the encoder, sigma is predicted by the encoder, epsilon is a random number. So now this is equivalent to randomly sampling from a distribution whose mu we are trying to force to be 0, whose sigma we are trying to force to be 1, and we are sampling a Z whose dimensionality is also 16 from this mu comma sigma distribution. And then that we can project back into 64-dimensional space. So now we have a token whose dimensionality is 64, sample from a latent space where latent space dimensionality is 16. But the data points in that latent space are kind of distributed in such a way that they have a mu of 0 and standard deviation of 1. Now what we do is, earlier what we were doing was, we had 64 spatial tokens which were passed into the transformer encoder, right? But this time, instead of 64 tokens, we will have 65 tokens. So 64 corresponding to spatial tokens and 1 token corresponding to this latent space projected into 64 dimensions. Now this 1 token is basically conditioned on the expert actions. So these expert actions are going as the input into the variational autoencoder, which has a multi-layer perceptron, which predicts 2 things, mu and variance of each dimensional 16. Then from that 16-dimensional space, we randomly sample 1. Then from that randomly sampled thing, we project back into 64-dimensional space. So now we have a 64-dimensional token. which will go with these 64 dimensional tokens. We have 64 tokens, each of which are 64 dimensions. So totally now we have 65 tokens, each of which have a dimension of 64. Now these 65 tokens will undergo what? Cross attention or self attention in the transformer encoder. It will undergo self attention, right? So these 65 tokens will now undergo self attention in the transformer encoder to produce 65 context vectors. How do we get expert action from ground truth? Yes, exactly. So this expert action is from the ground truth. Now, these 65 context vectors are one of the inputs that go into the transformer decoder. What is the other input that goes into the transformer decoder? Ideally, this arrow, instead of drawing it like this, it's better if I draw like this. So one of the inputs now that go into transformer decoder is the 5 action queries. The other input that goes into the transformer decoder is 65 context vectors corresponding, which comes out from the transformer encoder. Then there will be first self-attention, which is between these 5 action queries. Then there will be cross-attention between these 5 action queries and these 65 keys and 65 keys. Then there will be a dot product with or multiplication with the 65 values. So only difference now is because of this conditional variational autoencoder, the only additional thing that has happened is the conditional variational autoencoder will introduce an additional token Z, which is added or concatenated with the 64 tokens. So now you have 65 tokens. So now when the transformer decoder is performing cross attention is between these 5 tokens which are projected into query space and these 65 tokens which are projected into the key and value space. And then rest of the things are the same. Now one additional thing is in the loss. Now the total loss is, one is the reconstruction loss. What is the reconstruction loss? How much does the predicted actions compare with the ground truth action? So that is one loss. And then KL loss is how much your predicted mu and sigma. So you have predicted a mu and sigma here, right? How much your predicted mu and sigma varies from 0, 1. So KL divergent formula will be applied. But to not give the mu and sigma matching too much weightage, you multiply with the pre-factor of 0.01. So the total loss is a combination of you predicting the actions wrong and you predicting a mu and sigma which is not close to 0 and 1. So those two loss will be combined to produce the total loss, and this loss will be used for backpropagation in this architecture. And so in this architecture, now we have action chunking. You have transformer encoder TE. I'm just making up acronyms so that I don't have to write everything. You have transformer decoder TD. You have conditional variational autoencoder. What is missing is language. Language is missing, right? So this is the last step before we add the language part into the encoder. So now we need to put the language. One more thing is in inference part, there is no expert action available, right? So how do we get the Z? We just initialize Z as 0. From the latent space, this is not there. This connection is not there. We initialize the latent space such that Z is equal to 0. That 0 Z, which is a 16-dimensional vector, is projected into 64 dimensions. So basically you initialize a 0 vector and that is projected into 64 dimensions. And then that is passed into the transformer encoder as the last 65th token. Everything else remains the same. This is in the inference, because in the inference, this expert action is not available. In inference, there is no ground truth available. You are trying to predict something. So that is the only thing. So now we just need to add one last thing, which is the language. So let's see how language is added. So this formula, please don't get confused by seeing this formula. I already showed you this KL divergence formula. KL divergence formula is simply this. And if sigma 1 is equal to 1 and mu is equal to 0, you can simply substitute sigma 1 equal to 1 and mu 1 equal to 0. And you will see that the formula that results is similar to what I showed you here. Is similar to, in this code, this formula. It will be very similar to this formula, basically. Okay. So this is the KL divergence between two distribution. One distribution has a mu of mu, variance of this VAR. And the other distribution has a mu of 0 and variance of 1. So this is the formula for comparing two distributions in that fashion, KL divergence, and this will be multiplied by 0.01. Okay, so now let's see how to add language. Now, if we have vision only vision only action chunking transformer with conditional variational autoencoder, this is the simple architecture. I already showed this to you. Action chunks are passed into the during training into the conditional variational autoencoder, in which a multi-layer perceptron will project into two numbers. One is a 16-dimensional mu and 16-dimensional logarithm of variance. Then reparameterization is simply mu plus epsilon multiplied by sigma, where epsilon is a random number. So that is equal to z. This z is 16-dimensional. Then that 16-dimensional z is projected into 64-dimensional. If it is inference, none of this is there. If during inference, you directly start z equal to 0. Then that z token is actually passed into, I would say, this is not the most correct way to put it. You can say over here to make it 64 plus 1, 65 tokens, 64 spatial tokens plus 1. Okay, so this is the CNN layer. This is the transformer encoder layer with 65 tokens. So now you have 65 context vectors here. And now this is the transformer decoder into which 5 action queries are passed, which are each 64 dimensions. And there is a self-attention on between these queries and cross-attention between the 5 query tokens and 65 tokens coming from here, followed by an MLP head. MLP head will simply project 5 tokens of 64 dimensions into 5 tokens of 64 dimensions, and then 5 tokens into 4 dimensions. So now you have 5 tokens as 5 chunk size of 5 with forward, backward, left, and right. Okay. This also we already discussed. This is simple. I don't want to go through this, but now let's look at the language conditioning. Now, language conditioning, as I mentioned in the very beginning, you could add it in a few different places. So in the forked road, we can have vision only with language. In the curved road, we can have ACT without convolutional, without variational autoencoder with language. We can have ACT with conditional variational autoencoder and with language, right? So now we are going to see these three things, this, and this. So first, vision only model with language intent. This is very simple. You have already seen this in the last lecture. So vision only means first the camera input is converted into 64-dimensional vector with batch size B, to which we are simply concatenating a 32-dimensional language embedding. So language has only two intents. Intent 0 is take left. Intent 1 is take right. Then there will be an embedding like a dictionary, lookup dictionary, where there are only 2 items. Why there are 2 items? Because there are only 2 language intents. Item number 0 and item number 1. Each of these will be 32-dimensional. And this will be a learnable parameter, which is learned through NN parameter. And then what happens is, depending on which language intent you input, so if the language intent is 0, you will be picking the 32-dimensional vector corresponding to 0. So now it will be a 32-dimensional vector and batch dimension is also there. And then these two are concatenated. So 64 plus 32 will become a 96-dimensional vector and batch size B is there. So now in these 96 dimensions, we have vision plus language. Okay. So there is no cross attention or anything. It's simply vision and language. I hope you understand. And then these 96 dimensions in an action head is projected into 64 dimensions. So this is a multi-layer perceptron. So 96 layers fully connected with 64 layers following ReLU activation. Then those 64 are projected into 4 dimensions. And those 4 dimensions will now make up the 4 actions. That's it. So this is the simple vision plus CNN. If you want to run this experiment, just go to the same website. But instead of EXP1, just change it to EXP5. And in fact, I think this was actually pretty good in inference. Let me go to inference, load bundle JSON model, autopilot. So now see, this is not as smooth as the language conditioned action chunking transformer, but it's kind of working, right? You see this, it's kind of working. So this is the left intent. And let's go back to the write intent. So write intent means, see, it corrected its mistake. It initially started with left, but then I changed the intent to right, and it's going through the right. Here, there is no action chunking happening. There is absolutely no transformer architecture. There is no conditional variational autoencoder. The only thing that exists here is the language intent addition added to the vision encoder. You can try this. The notebook is also provided here. Now, the last thing, which is not last thing, second last thing, this is ACT, conditioned on language, but without the conditional variational autoencoder. Please don't get intimidated by seeing the diagram. It's very simple. Okay. So part number one. Part one is already, vision passed through CNN layers. Now you have 64 spatial tokens. Similarly, language is converted to 32 dimensional tokens or 64 dimensional tokens, anything which you wish. But there is only one language token. But here there are 64 spatial tokens. So now you add those two tokens, or you concatenate those two tokens to finally have 65 tokens, each whose dimensionality is 64. Now in transformer encoder, these 65 tokens will perform self-attention with each other to produce 65 context vectors. Then it comes to transformer decoder. In decoder, only one difference compared to earlier part is, you have 5 action queries of dimensionality 64. But to better condition these action queries, to each action query, you have 5 of them. To each action query, you add the language token also. So the language token is 64 dimensional and you have only one token, but here you have 5 action queries. So to each action query, you just add the language token also. So it's not concatenation to produce 6 tokens, this addition. So the language token is added to each of these. So it's basically injecting language into the query also. Then there will be first self-attention between these tokens, these query tokens conditioned on language. Then there will be cross-attention between these 5 tokens conditioned on language, plus these 65 tokens where both language and image are present. There will be cross-attention, resulting in finally 5 context vectors whose dimensionality is 64, which you project into 64 dimensional layer following ReLU. Then from there, you project into 4 dimensional layer followed by ReLU. So now you have finally 5 action chunks, each with 64 dimensions. So the only difference now here is this language injection. So language injection makes the number of tokens, instead of 64, it will be 65. And here also you inject the language. So now I have a question. If conditional variational autoencoder is also present apart from this language, where will the numbers change? In the input that goes into the transformer encoder, what will be the number of tokens if CVAE is also there? What will be the length of the tokens? Exactly, it will be 66. 64 image tokens, 1 token corresponding to the Z, which is coming from the latent space, 1 token corresponding to language. So totally there will be 66 tokens. You will also see that in the code. So in the code here, where is the, in this encoder input, torch.cat means torch.concatenate. This X is the image tokens. This is the language token, and this is the Z tokens. You are concatenating them together to produce 66 tokens. So I'll show you that architecture also. Now I don't even have to show you, you already understand, but I'll just show you. So this is now the architecture. This is the final proper architecture which worked for me. I'm sure this can be done in many other ways also, but after a lot of experiments, I figured out this works really, really well. So input module, result is 64 tokens. Language module, result is 1 token of dimensionality 64. Conditional variational autoencoder, which again results in 1 token, which is Z of dimension 64. So you have 64 token plus 1 token plus 1 token. So total 66 tokens. And though they are going into the transformer decoder, transformer decoder also gets one other input, which is CVAE. The input from CVAE, input from language token plus queries, not CVAE, my bad. So query, you have 5 tokens, each dimension 64. To each of these tokens, you add the language conditioning. So you have again 5 tokens, but modified with the language intent with 64 dimensionality. They are passed here. self attention between these 5 tokens, cross attention between these 5 tokens, and these 66 tokens happen in the transformer decoder, resulting in 5 context vectors, 64 dimensions. These 64 dimensions are projected into 64 dimensions itself once, followed by ReLU. Then it is projected into 4 dimensions. Now these 4 dimensions are now passed through sigmoid to produce the 4 actions. But then like that, you have 5 length of 5 for next 5 time steps. So each of them will be, sigmoid will be applied for each of them. In training, you will have cross entropy loss plus the KL divergence loss. So this is the complete action chunking transformer architecture conditioned with language. Now, did any of you try running this? At the start of this lecture, I had asked you to just run this. If any of you tried to run this, just let me know and share the model.json with me. I can try inferencing on your model. Okay, Arya, can you just share the model.json here in the chat so that I can download it and I can try inference on your model just to see how it works. And while you do that, let me also explain this code. So the code is very simple. It looks complex, but it's actually simple. This part is just for uploading all the JSON files corresponding to training. So I have 47 training dataset files, which are downloaded from this 3D simulation environment. And Arya, just in case if you are not able to share the thing directly in the chat because of the file size or something, you can just create a Google Drive folder, make the file visible to all. Just share the link here so that everyone can try inference. And then image size is 128 by 128, chunk size is 5, action dimension is 4, forward, left, right. Okay, Arya has shared the model.json. Let me download it. This is for experiment. Okay, Suresh has shared it. This is for experiment number 9, right, Suresh? EXP9, this one, right? Okay, awesome. Let me try the model.json. So now for me to try Suresh, the one provided by Suresh, I just need to click drop model.json. And in my downloads, I have the model here. And then autopilot. I hope this works. Let's see. So intent is left. Yeah, it's working perfectly. It's amazing. See how smooth the driving is. If you try with the rest of the models, it's not this smooth at all. And it's a bit slow because I'm running the inference in JSON. Later, I plan to deploy a Python server to which you can connect using the, using this local host or using a URL. Let me change the intent. This is really, really good training. Amazing. Now, if it is right, see, I did not change it to right initially. It was left, then it went to left. And now in between, let me try changing to left to see if the car will go to left. Because now I changed my language intent and see the car is, okay, it's not fully figuring out its left, but somewhat. But you see, it's driving on the right. It's really beautiful. I'm so happy to see this. So this should have taken you maybe 15 or 20 minutes to execute. Okay, let me try Arya's code also. It should be similar. I don't think there should be any difference because you have not changed anything in the training code. But let me just try it regardless. Okay, this one model 13.json. Autopilot. Yeah, it's working beautifully. So in the last lecture, because this website was loading so slow, I had made a lot of changes to optimize its speed. If I use the same website as last time, it would have been so slow. So I have made a lot of changes in the way this 3JS renderings happen. Let me also change the language intent. I just want to test the left. Yeah, it's working really, really well. This is awesome, guys. Everyone should try this. I think it's a beautiful experience to run your code and see something like this work. So yeah, I think we discussed that. So now let's see how the code is, right? So action dimension is 4, forward, left, right, and back. Back is never used. D model is dimensionality in the embedding space, 64. Number of attention heads is 2. Number of encoding layers in the encoder, number of transformer blocks in the encoder, which is only 1. Decoder also, it's only one. FFN multiplier is feed forward. The multi-layer perceptron in the transformer has a multiplier which projects from 64 dimensions to 128 dimensions. That is 2. Spatial, n spatial is number of spatial tokens. It is 64. Latent dimension is the dimensionality of the Z space where mu and sigma is residing. It is 16. This is the KL divergence weight multiplier for the loss function. Epochs is 200, batch size is 16. Okay, then you just load the data. This is just for creating the data set of images originally in the base 64 format. If you remember, in the JSON file, it's encoded in the form of base 64. We need to convert it into a format which can be accepted using tensor. So this block of code is just for that. So I don't want to spend time on this, but the place where I want to spend time is this block, of course, because this is where we define the language conditioned action chunking transformer with conditional variational autoencoder. So this now you will, okay, let's not go through this. Let's not go through the definition part. Let's go through the forward pass. I'm sure you all understand what's going on. What are these five or these 5 lines of code? What is these 5? You already know it. It's the convolutional neural net 2D CNN with ReLU activation. After each CNN, there is ReLU. So self.conv1 followed by self.ReLU. Then again, self.conv2 followed by ReLU. Okay, so this is that. And then there is a flatten followed by spatial position embedding. So this flatten followed by spatial position embedding is basically you convert 64 2D tokens into 64 one-dimensional token, but then you add spatial position embedding, which is just what you do before passing into transformer encoder. Then you have a language embedding, not function. You have defined the language embedding over here, which is an embedding where you have number of intents is 2, dimensionality of the model is 64. So it's just a learnable embedding, not learnable embedding. It's an embedding layer which will project into 64 dimensional. It will pick from one of the two. So if the language embedding intent is 0, it will pick the first row. Otherwise, it will pick the second row. Then, so this is that. Now, what about this mu and logarithm, variance of logarithm? Why do we need this if-else condition? This I hope you understand. Mu comma logarithm of variance is self.encode z of action chunk. Now encode z, obviously we should have a function over here. This is encode z. So action chunks are flattened using a conditional variational autoencoder's encoder part, which is again defined here. It's very, very simple. It's just a linear layer going from action dimension into chunk size, because you have chunk size of 5, action dimension is 4. So this will be 20. Dimensionality of the model is 64. Then from dimensionality of the model, you go to latent dimension, which is 16, right? Yeah, I already shared the code with you. The code is here only in this EXP9 VLA. This, if you click this collab notebook, you can download the code. So that is the conditional variational autoencoder latent dimension, and CVAE logarithm is also the same. So basically in the CVAE logarithm of variance, basically it's residing in the latent dimension only. So these two things are two parameters which are predicted by the multi-layer perceptron, both residing in the latent dimensional space. And then Z project is you are projecting whatever you pick from this space from latent dimensional to 64 dimension. Latent dimension is 16. So now my question is, why do you need this if-else condition? We already kind of discussed this. When is if activated? When is else activated? Exactly. So when do you think action chunk is present? During training, action chunk is present. During inference, action chunk is not present, right? So this this is basically during training, your Z will be, you randomly sample from your mu comma sigma, I mean mu plus epsilon sigma, and then you reparameterize it. Basically, Z is equal to mu plus epsilon sigma. Where is that? I think it's here. Yeah, this one. Reparameterize. So standard deviation is sample from your logarithm of variance. Epsilon is the random number. So now your reparameterized number Z equal to mu plus epsilon multiplied by sigma. Sigma is the standard deviation. Now, once you have this, your Z token is whatever is there in your latent space projected into 64 dimensional space. Now, encoder input will have 66 items, 64 coming from language. This is X. Sorry, not language, vision. 1 coming from language, and 1 coming from latent space. Latent space projected into 64. Okay. So this is the final concatenated token sequence going into what? This goes where? This encoder input. It goes into the transformer encoder. So now this is the transformer encoder part. Memory is simply you store the output of the transformer encoder so that it can be later passed into transformer decoder. Okay. Now transformer encoder definition, where is that? Transformer encoder definition is here. We are using the native transformer encoder from this nn dot module. So nn dot transformer encoder, where we say encoder layer is 1. No, encoder layer is this. Encoder layer is what we pass as the encoder, where dimensionality of the model is 64. Number of attention heads is 2. Dimensionality of the feed forward is 64 multiplied by 2 because this FFN multiplier is 2. Dropout is not there. Batch first equal to false means the first dimension is the token sequence. It's not the batch. But in many cases, depending on the way you write the code, this you will have to put as true. Otherwise, you will not get the output. So it depends on whether sequence or batch, whichever is fed first into the transformer. If you don't put anything like this, by default, it will take token sequence as the first dimension, the transformer encoder layer. It's a minor artifact. You don't have to worry about it. Then decoder layer is also the same, nn dot transformer decoder layer. But in transformer decoder, you have same number of layers as that of the encoder. And number of layers is equal to 1 because you're having only one single transformer decoder block. And this is where you pass your encoder input into transformer encoder, and then you have the decoder part here. So to the transformer decoder, you will pass two things. You will pass the output of the transformer encoder. You will also pass the queries. Okay, so queries, comma memory. So the output of the transformer encoder is called memory. These queries are these self.action queries. Plus and action queries are conditioned on language. So you see this plus language. So this is what we saw here. Action queries in this image. See this, action queries are conditioned on language. So that is what you see in this part of the code. These are action queries plus language conditioning. And then those two, the output from the encoder and the action language conditioned queries are passed into the transformer decoder, queries, comma memory. And then you finally have the logits. The logits are after the action head. Action head is simply this guy. This is the action head. Action head simply projects 64 into 64. Then that 64 is projected into 4. And yeah, that's pretty much it. And then the logits, return logits, comma mu, comma logarithm of variance. You know why these three things are returned? Can anyone tell me why do you have to finally return from this class logits, mu, and logarithm of variance? We discussed this. Think about what is this used for in training? No, it's not for inference. It's for training. See, in training for calculation of loss, you have two losses. One is if the logits are far away from your actual ground truth actions. Mu and logarithm of variance is for KL divergence. So for the total loss, which includes the difference between the predicted actions and real actions, the ground truth actions, for that, plus the predicted mu and predicted logarithm of variance to see how much they deviate from 0 and 1 in the KL divergence formula. Okay, so that's why you return these three things. And then that's pretty much it. Yeah, and this is the KL divergence formula, which we'll be calling during the loss calculation part. And then you have loss calculation, the total loss you can see over here. So total loss is the reconstruction loss, which is the loss, the binary cross entropy loss due to wrong prediction of actions. And KL loss is multiplied with the KL weight. KL weight, where have I defined? Let me check. It should be 0.01 or something. Yeah, so KL weight is 0.01, meaning you are not extremely giving weightage to the fact that you are deviating from mu equal to 0 and sigma equal to 1. Because if you keep this weight as 10 or something, your model will not learn to predict actions really well. It will make the latent space perfect. It will make the latent space such that mu equal to very close to 0, sigma equal to very close to 1. But your actions will not be perfect. That's the reason why you put a bit low weightage. You will see one more multiplier in the transformer part. Where is that? Yeah, this one. So you will see here that the action queries are the initialized action queries are multiplied by a number called 0.02. I mean, this can be 0.02 or any small number. Basically, what we are doing here is action queries, when they are initialized as random numbers. Okay, random numbers whose distribution is between 0 to 1. The mean is 0, standard deviation is 1. So what we are doing is, to make sure that action queries are not like random big numbers, we are just multiplying by a smaller number here, 0.02. I saw that this was helping. I tried without this also. I think it may work. I'm not 100% sure. I tried with different numbers. Initially, I started like this only. Then I realized that maybe my action queries are too biased to be large. So I realized that adding this is better. But this I have not seen in papers. Okay. So this is not something which is there in paper. It's just something which I saw work better. Same thing you will see in one more place. In the language part, in the spatial position embedding part here. So when we are adding spatial position embedding, there also we are initializing the embedding in the spatial embeddings as random numbers. But then those random numbers we are multiplying by 0.02 so that we are not giving excessive importance to spatial position embedding numbers. So my thinking is this probably we can remove and still the code might work. But this we might want to keep because position embedding should not overwhelm the actual language intents. So because these position embeddings are added to language intents, so it should not overwhelm it. But we can try. There are different options, right? This is not a model which is something like a gold standard or anything. We can try various things as part of our ablation studies. But at the end of the day, the models are giving really good accuracy. I'll show you one table. So this is the table where I conducted 9 experiments. So in 3 experiments, I had curved road. In 6 experiments, I had forked road. In curved road, there was no language intent because there is only one. So all of these are no. Language intent is not there because there is only one way in which you drive. But in curved road, 2 of them had action chunking transformer without language, in which one of them had conditional variational autoencoder, the other one did not have. The accuracy in all these cases in general from my experiments were in general between 89% and 94%. It doesn't mean that unlike classification or something, see in classification, the thing is, if something gives you 90% accuracy, you will almost always get good predictions. But in driving or in robotics, an validation accuracy of 90% is not much. The reason is each mistake, if you make a mistake, it can get compounded. So it's very difficult to say that validation accuracy of 94% means inference is really good. There is no such guarantee. If it pushes to very high numbers, it's probably possible, but I tried my best. I could not really get it above 95%. If any of you manage to do it, just let me know. I'll be so happy to try your model. The best model is this guy, action chunking transformer with language, with conditional variational autoencoder. Not in terms of validation accuracy. In terms of validation accuracy, it is a bit low. But in terms of actual inference, in terms of real inference, this guy performed the best. In terms of inference, for me, in fork road, this was really bad, if I'm not wrong. Although the validation accuracy was very, very good. In inference, this guy was driving very, very bad. If I'm not wrong, I can just quickly check. Experiment number 7. Yeah, you see, it was really bad inference. But somehow in the training part, the validation accuracy was really good. So that's the reason why I say validation accuracy does not mean much in inference in robotics. I don't know why. Maybe because my training data is not diverse enough to capture every single possible failures. Maybe that's the reason. It's very difficult to say. But as we expect, this model has worked the best. In curved road, I saw that again, just ACT with conditional variation autoencoder was not the greatest. Vision alone was okay. In fork road, vision alone plus language embedding actually worked surprisingly well. Because can anyone tell me here, vision only plus language embedding, how does it capture the bimodality? because there is no conditional variation autoencoder. So where is bimodality getting captured? It is getting captured in the fact that there is language embedding, right? Because language embedding inherently are two types. So when you are adding that with vision, that bimodality is already coming into the input. But ACT alone without conditional variation autoencoder, not good enough in inference. I did not see that. So this validation accuracy is very, very deceptive. Although I use pretty much the same training data. So now I'll tell you for which the training data was the same. For vision only. So the training data for all these, for all vision only, it was the same. So meaning for this, let me just erase everything. So training data for all these experiments plus these two experiments were the same without any language intent. Actually, you know what? Not the same. My bad. For these three, it's the same because this is a different map. For this plus these two, it was the same. So I had one set of training data for this, another set of training data for these three. Then I had another set of training data for these three where it is forked road with language intent. So I had basically three different sets of training data for these three experiments. And this is what I received. So now what I urge you to do is try your own training. The code for everything, all you need to do is like change the URL here, x1, change it to, it goes from x1 all the way till x9 for these 9 experiments. My model, my code, my training data, and my trained model, all three things are provided. So if you want to download my trained model, just click this. If you want to load it for inference, just go to inference and just click load bundle model. It will automatically load it without having to download it. You can try your own experiments and come up with your conclusions. Okay. So I'll be posting an assignment related to this for you to try this week. But I think we can stop today's lecture here. So my goal was for you to try out action chunking transformer, understand how it is applied here. And the vanilla action chunking transformer, ACT action transformer paper. If you look at this one, this paper was published, I think, in 2023. This is where action chunking transformer was tried for robotics. I don't think many people have tried ACT for self-driving yet, but in ACT, so that's the reason why we had to come up with our own architecture. So I'll show you their architecture in the supplementary. So Saurav, Collab notebook is there in the website link itself. You can download directly from there. But let me show you one last thing, the ACT architecture in the supplementary. Yeah, this one. So this was the architecture. Okay. So there you have 4 cameras. So you have 4 vision embedding heads, and then the camera inputs are concatenated. Then here one additional thing that is concatenated. Here there is no language intent, by the way. So this is not a vision language action model. It's just a vision model for robotics. Here joints, the current joint positions are also input into the transformer encoder. What is the equivalent of this in driving? Equivalent of joint position. In a robot, the joint position are between different arms. There is a joint position, right? Motor position. I have 2 questions. What is the equivalent of that in driving? And why did we not use that in our transformer encoder? You never saw me passing the steering position or something into the transformer encoder. Why not? It's not a answer. It's not a question with a very definitive answer. But in your opinion, I'm asking your opinion. In your opinion, in which case is knowing the steering or knowing the motor position so important? Is it in robotics or is it in driving a car? Like knowing the current position. Think about this. In robot, if there is a camera and if something has to be picked up, the robot really, the position of the robot itself is the joint positions, right? The location of the joints of the motor. But car is different. Car is moving in the real world. So the car's position can be the same irrespective of so you could park a car and start it such that the steering is fully rotated to the left or fully rotated to the right. The steering's rotation is kind of a little bit decoupled from where the car is in the real world, right? Which means it's not as important for a car to pass the current steering location into the transformer encoder as much as passing the camera view. Of course, if we can pass it as an extra token, I don't think there is any issue. But in our case, the action tokens that are predicted are simply, it's not the joint angle or anything. It's like left, right, back, and forward. Those actions. We don't need to pass the current set of actions into the transformer encoder. It's not really useful for predicting the future set of actions. What is more useful for predicting the future set of actions are two things: vision and the language intent. So that's the reason why in our model, you will not see this thing. But Z, you see this Z, which is concatenated along with the rest of the tokens that we also have. So we had 65th token as Z, 66th token as language. Here, if we talk in terms of 64 language tokens, it's not 64 by the way, but if it was 64, 65th is the joints, 66th is the latent variable, Z. And then the output, which are the 66 tokens, which are resulting context vectors, are passed into the transformer decoder. And decoder has one more input. Now, what are these inputs? In our case, these were the 5 action chunks. Here, these are the action chunks corresponding to the decoder. So almost the same architecture. The only difference is the absence of joints. Now, how do we get data sets to train the TurboPy car? Very good question. So for TurboPy, none of these data set will be useful. The reason is in TurboPy, the final action are 3: Vx, Vy, and omega. So it's a 3-dimensional action. It's not 4-dimensional. So for TurboPy, what we will do is, for those of us who have the TurboPy, we will train it from our place. I'll tell you what all things to set up. We will train it and we will collect the data by teleoperation. So it will be the camera plus the camera view plus the language, which we will collect for TurboPy when we'll train it. We'll discuss all of that in the upcoming lecture. So far, we haven't touched TurboPy, but the reason for that is we need to have some base before that. Do we use Carla sim? I have realized that Carla is very difficult for most people to run. The computational resource needed for that is insane. Plus, whatever we do in Carla is not applicable for TurboPy, because Carla is like a real world kind of setting. TurboPy is like a different setting. We tried gazebo simulations for TurboPy, like other 3D environments for TurboPy. We can try that, but Carla is more for real world. So TurboPy is not something which lives in real world, right? So Carla would have been very good if you were, let's say, if we had access to some sort of physical big car, big actual driving car, something like that. But that's the reason why we won't go with Carla. So I'm still figuring out which 3D environment to use for TurboPy, for actually simulating TurboPy. I can build a custom 3D environment myself where actions are not, forward, backward, left, and right. Actions are rather Vx, Vy, and omega. And then I can try to make the custom environment such that it mimics our office or our houses, something like that. I'll try something like that, or I'll try a different environment like gazebo or something like that. So I'll let you know. But in any case, try to get your TurboPy within the next 1 to 2 weeks. We'll be slowly moving into actually training the TurboPy. Rest of the things regarding the links of purchase, everything I have mentioned in the Discord. Yeah. But the thing is, this bootcamp is not about Carla, right? This bootcamp is about physical robotics. It's not about simulation. It's not about vision simulation. If you want to do physical robotics, you have to have a physical thing. The good thing about SO101 is the actual thing which you can buy for $200 is almost same. It's a 6 degree of freedom one, similar to a $40,000 thing. In the car, there is no such equivalent. The car which costs, a self-driving car which actually costs maybe $50,000, $60,000 versus the self-driving car which you can buy, are completely different things. It's a hugely different scale. For that reason, whatever training data we get from the internet, whatever training data we can get from Carla, we won't be able to apply to TurboPy because it's a small thing. It's looking at such completely different view. So that's the reason why we'll have to construct our own training data. We won't be able to use training data from the internet unless someone has already constructed it and something is available on GitHub. I have searched for it. I have not found it yet. If any of you find it, please share it with me. I'll be happy to incorporate it. But thank you so much, everyone. I know that today's lecture extended by at least 1 hour, but I'm thanking you for staying back so late. We will meet again next Saturday. I hope you learned a little bit about action chunking transformer. For future questions, just email me or put it in Discord. And please get the TurboPy ready in the next by the next couple of weeks. If you are shipping to India, it will take at least 2 weeks from my experience. Sometimes it will get stuck in customs. You have to give your KYC and all those things. If you are shipping to US, it's different. So it depends on your physical location. But thank you so much, everyone. Let's meet next Saturday. Take care until then. Try out these experiments yourself. The code, please try running yourself. Try some ablations, making changes in the code, etc. Take care. Have a good weekend. Bye.